Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 283, Move Zeros. This is a popular problem that tests your ability to manipulate arrays efficiently. Stick around as we break down the problem, explore different approaches, and learn valuable tips to solve it. Let's dive in. In this problem, we're working with an array manipulation task called Move Zeros. The goal is to take an integer array, nums, and modify it in place so that all the zeros in the array are shifted to the end, while still maintaining the relative order of the non-zero elements. A key point here is that the modification must be done in place, meaning you cannot use additional memory to create a copy of the array. Additionally, the solution should aim to use the minimum number of operations. Let's look at the input and output format. The input is an array nums with a length ranging between 1 and 10,000, and the output is not a separate value but the modified version of the same array. For example, if the input is nums equals 0, 1, 0, 3, 12, the output should be nums equals 1, 3, 12, 0, 0. This result is achieved by moving the zeros to the end while maintaining the order of non-zero elements. In the example nums equals 0, 1, 0, 3, 12, the 0 at index 0 is moved to the end of the array, and the 0 at index 2 is also moved to the end. Meanwhile, the non-zero elements, 1, 3, 12, retain their original order. Now consider another case where the input is nums equals 0. Since the array contains only one element, and that element is 0, there's nothing to rearrange, so the array remains unchanged. Lastly, in the example nums equals 4, 2, 4, 0, 0, 3, 5, 1, the two zeros at indices 3 and 4 are shifted to the end of the array. The non-zero elements, 4, 2, 4, 3, 5, 1, remain in their original relative order, resulting in the output nums equals 4, 2, 4, 3, 5, 1, 0, 0. To ensure a clear understanding of the problem, let's highlight the constraints and edge cases. First, the array length is guaranteed to be between 1 and 10,000, and each element in the array falls within the range of -2 to the power of 31 to 2 to the power of 31, 1. The modification must be done in place, meaning you cannot allocate extra memory for a copy of the array. Additionally, the relative order of non-zero elements must be preserved after moving the zeros. For efficiency, the solution should run in O(n) time complexity and use O(1) extra space. Now, consider some edge cases. If the array consists entirely of zeros, such as 0, 0, 0, the array remains unchanged. Similarly, if there are no zeros, like in 1, 2, 3, the array stays the same. Single-element arrays, whether zero or non-zero, also remain unchanged. Lastly, arrays with zeros at the start or end, such as 0, 0, 1, 2, or 1, 2, 0, 0, should still preserve the relative order of non-zero elements while moving all zeros to the end. To solve the Move Zeros problem, let's first consider the brute force approach. The intuition here is straightforward. We iterate through the array, collect all non-zero elements into a temporary list, and then append zeros to the end to match the original array length. This involves two main steps: first, creating a new list of non-zero elements, and second, filling the remaining positions with zeros. While this approach is simple and easy to implement, it comes with some trade-offs. Specifically, it requires additional space to store the temporary list, which violates the problem's in-place constraint. In terms of complexity, the time complexity is O(n), since we make a single pass to collect non-zeros and another to append zeros. However, the space complexity is also O(n), due to the extra storage required for the temporary array, making it less optimal for this problem. Now, let's explore a more efficient solution using the two-pointers approach. The intuition here is to use two pointers to traverse the array in a single pass. One pointer, called last_non_0_index, tracks the position where the next non-zero element should be placed, and the other pointer, current, scans through the array. Every time we encounter a non-zero element, we swap it with the value at the last_non_0_index and then increment the last_non_0_index. This ensures that all non-zero elements are moved to the front of the array while maintaining their original order. The key advantage of this approach is that it satisfies the in-place constraint, as no extra space is used. Additionally, the time complexity is O(n) due to the single traversal of the array. However, one trade-off is that the frequent swapping of elements may slightly increase runtime in some cases, though this is generally negligible. Another optimization to consider is the shift non-zeros approach. This method avoids unnecessary swaps by directly shifting non-zero elements forward and then filling the remaining positions with zeros. The process involves two distinct loops. In the first loop, we iterate through the array, and for each non-zero element, we place it at the last non_zero_ index, incrementing this index as we go. After processing all elements, a second loop fills the rest of the array with zeros, starting from the last non_zero_ index. This approach minimizes the number of write operations, making it efficient in terms of performance. It also maintains the in-place requirement, as no additional space is used. The time complexity remains O(n) due to the two linear passes, but the trade-off is that it requires explicitly separating the logic into two loops, which may slightly increase implementation complexity. Among the approaches discussed, the chosen strategy is the optimized two-pointers approach. This method strikes the right balance between simplicity and efficiency. It achieves a time complexity of O(n) while adhering to the in-place constraint, making it both effective and concise. Unlike the shift-based solution, it avoids the need for a second loop to fill zeros, which simplifies the implementation. The key insight that makes this approach work is recognizing that non-zero elements must retain their relative order, and this can be achieved by moving them forward one at a time. By using two pointers, we efficiently track both the insertion point for non-zero elements and the current position being evaluated, enabling a single-pass solution. While it may involve more swaps compared to the shift-based approach, this trade-off is negligible for most practical input sizes. Ultimately, the two-pointers approach provides an elegant and optimal solution to the problem, satisfying all constraints while being easy to implement. In this problem, we are tasked with moving all zeros in an array to the end while keeping the relative order of all non-zero elements intact. The challenge is to solve it in place, meaning we cannot use any additional memory beyond a constant amount. This ensures the solution is both space-efficient and optimized. To begin, we need to understand the constraints. The order of non-zero elements must remain unchanged, and we have to use only the given array for all modifications. Additionally, the array can consist of any integer values, positive, negative, or zero. To achieve this efficiently, we'll use a two-pointer approach. The first pointer, non_zero_idx, will track the position where the next non-zero element should be placed, starting at index 0. The second pointer, I, will iterate through the array, identifying non-zero elements. As I move through the array, we'll ensure that all non-zero values are moved to the front sequentially, minimizing unnecessary operations. Now, for the actual iteration process, as we traverse the array using the pointer I, we check the value at each index. If the element at I is non-zero, we swap it with the element at the non_zero_idx position. This ensures that non-zero elements are moved forward, one at a time, without disrupting their order. After the swap, we increment the non_zero_idx pointer to prepare for the next non-zero element. If the element at I is 0, we simply skip it and continue iterating. By the end of this loop, all non-zero elements will have been shifted to the front of the array, and the non_zero_idx pointer will point to the position where the first zero should be. At this point, if needed, we can overwrite all remaining positions from non_zero_idx to the end of the array with zeros. This step may be considered optional since the zeros are already at the end, but it ensures clarity in the final output. The key insights here are the in-place optimization, where we rearrange the array directly, and the two-pointer approach, which minimizes the number of operations. Furthermore, the algorithm naturally terminates early in scenarios where there are no zeros, making it highly efficient. This solution relies entirely on the input array, which is modified directly in place, eliminating the need for any additional data structures. The two-pointer technique is the core of this algorithm, with non_zero_idx keeping track of where the next non-zero element should go and I scanning the entire array. The main operation here is swapping. When a non-zero element is encountered, it is swapped with the element at non_zero_idx, which ensures that non-zero elements are placed in their correct positions. This swap operation is highly efficient, taking constant time, O(1). Another key advantage of this algorithm is its single-pass nature. The loop iterates through the array just once, making the time complexity linear, O(n). Since we're working in place without any additional memory, the space complexity remains constant, O(1). This balance between time and space efficiency makes the algorithm highly optimized. To better understand how this works, we'll walk through an example to see the algorithm in action step by step. Consider the input array nums equals 0, 1, 0, 3, 12. We start by initializing non_0_idx to 0. The pointer I begins iterating from index 0. At I equals 0, the element is 0, so no action is taken. Moving to I equals 1, the element is 1, which is non-zero. We swap it with the element at non_0_idx, which is also 0. The array now becomes 1, 0, 0, 3, 12, and we increment non_0_idx to 1. At I equals 2, the element is 0, so we do nothing and continue. At I equals 3, the element is 3. We swap it with the element at non_0_idx, giving us 1, 3, 0, 0, 12, and increment non_0_idx to 2. Finally, at I equals 4, the element is 12. Swapping it with the element at non_0_idx results in 1, 3, 12, 0, 0. At this point, the loop ends, and the array has been successfully rearranged. The zeros are now at the end, and the relative order of non-zero elements is preserved. This step-by-step process ensures correctness and efficiency. Some important edge cases to consider include arrays that contain only zeros, where the algorithm simply iterates without making any changes, and arrays with no zeros, which are returned as is. For edge cases, if the array contains no zeros, such as nums equals 1, 2, 3, the algorithm processes each element normally, but no swaps are necessary, and the output remains 1, 2, 3. Similarly, for arrays with only one element, such as nums equals 0, the array is already in its correct form, and no changes are needed. These scenarios highlight the robustness of the algorithm in handling various inputs efficiently. To implement this solution in Python, we can use the following code: initialize non_0_idx to 0, and iterate through the array with a for loop. For each non-zero element, swap it with the element at non_0_idx and increment non_0_idx. At the end of the loop, the array will have all non-zero elements at the front and zeros at the back. This simple yet effective implementation ensures that the task is completed in O(n) time with O(1) space complexity, making it highly optimized for large inputs. This Python solution uses an in-place approach to move all zeros in the array to the end while maintaining the relative order of non-zero elements. We define a variable non_0_pos, which serves as a pointer indicating the next position to place a non-zero element. Initially, it is set to 0 because no non-zero elements have been processed yet. The algorithm iterates through the array using a for loop. For each element at index I, it checks if the current element is non-zero. If it is, the code swaps the current element nums, I, with the element at the non_0_pos index. This ensures that non-zero elements are shifted to the leftmost portion of the array. After the swap, non_0_pos is incremented to prepare for the next non-zero element. If the current element is 0, the loop simply continues without any changes, as zeros are intended to remain in place until all non-zero elements have been shifted. This approach processes each element of the array exactly once, resulting in an O(n) time complexity. The solution uses O(1) additional space, meeting the problem's constraints for in-place operations. The relative order of non-zero elements is preserved because we always swap the current non-zero element with the first available zero position without disturbing the sequence of previously processed elements. This is the Java implementation of the move zeros problem from LeetCode. The logic mirrors the Python implementation provided, using a pointer to track the position for the next non-zero element. Key differences include the use of static typing in Java's array manipulation syntax. This method iterates through the array once, making swaps as needed, and achieves O(n) time complexity. Here, we start with the input array nums equals 0, 1, 0, 3, 12. The goal is to move all zeros to the end while maintaining the relative order of non-zero elements. First, we initialize a variable non_0_POS to 0. This variable tracks the position where the next non-zero element will be placed. We then iterate through the array. At index 0, the value is 0, so we do nothing and move to the next index. The state of the array and non_0_POS remains unchanged. At index 1, the value is 1, which is non-zero. We swap nums 1 with nums non_0_POS, effectively placing 1 at the beginning of the array. After the swap, we increment non_0_POS to 1. The updated state is nums equals 1, 0, 0, 3, 12. Next, at index 2, the value is 0, so again, no action is taken. The state remains the same. Moving to index 3, the value is 3, which is non-zero. We swap nums 3 with nums non_0_POS, placing 3 after 1. We then increment non_0_POS to 2. The array now looks like nums equals 1, 3, 0, 0, 12. At index 4, the value is 12, which is non-zero. We swap nums 4 with nums non_0_POS, placing 12 after 3. We then increment non_0_POS to 3. At this point, the array is fully processed, and all non-zero elements are correctly positioned at the front, with the zeros moved to the end. The final state of the array is nums equals 1, 3, 12, 0, 0, and the value of non_0_POS is 3. The output for this example is 1, 3, 12, 0, 0. Now, let's consider another input where the array contains only zeros. For nums equals 0, 0, 0, 0, we initialize non_0_POS to 0 and iterate through the array. At each index, the value is 0, so no swaps are made, and non_0_POS remains at 0 throughout the process. As a result, the array state doesn't change, and the final output is 0, 0, 0, 0. In the last example, we have an input array where all elements are non-zero, nums equals 1, 2, 3, 4. Here, we initialize non_0_POS to 0 and begin iterating. At each index, the value is non-zero, so each element is swapped with itself, and non_0_POS is incremented by 1 after each step. At index 0, the array remains unchanged as nums equals 1, 2, 3, 4, and non_0_POS becomes 1. Similarly, at index 1, the state is still nums equals 1, 2, 3, 4, and non_0_POS is updated to 2. At index 2, the array remains nums equals 1, 2, 3, 4, and non_0_POS is 3. Finally, at index 3, the array stays the same, and non_0_POS becomes 4. Since all elements were already non-zero, the array didn't require any changes, and the final output is 1, 2, 3, 4. To analyze the time complexity of the algorithm, we start with the fact that it processes the array nums in a single pass. This means the for loop runs exactly once for every element in the array. If the size of the input array is n, the loop will iterate n times. Inside the loop, we find a swap operation that is executed only when the current element is a non-zero. Even in the worst-case scenario, where all elements are non-zero, the swap operation is performed n times. Importantly, each swap operation takes constant time, or O1. As a result, the overall time complexity is determined by the n iterations of the loop, each with an O1 operation, giving us a total time complexity of O(n). This makes the solution highly efficient when processing larger arrays. Now, let's examine the space complexity of the algorithm. The key advantage here is that the algorithm modifies the input array nums in place, meaning no additional memory is allocated for creating a copy of the array. The space used by the input array is proportional to the size of the input, O(n), but since it is not additional space, we don't count it in the space complexity. Aside from the input array, the algorithm uses a single integer variable, non_0_POS, to track the position for the next non-zero element. This variable requires constant space, or O1. Therefore, the algorithm does not allocate any extra memory and achieves an overall space complexity of 1, making it highly space efficient. Let's break down the algorithm's complexity further by considering the best case, average case, and worst case scenarios. In the best case, where all elements in the array are non-zero, such as 1, 2, 3, 4, the loop iterates n times, and each iteration performs a swap. This results in a time complexity of n. In the average case, where the array contains a mix of zeros and non-zeros, like 1, 0, 2, 0, 3, the loop still iterates n times, with some iterations performing swaps. The time complexity remains n. In the worst case, where all elements are zeros, such as 0, 0, 0, 0, the loop again iterates n times, but no swaps are performed. Even so, the time complexity is still n. Across all scenarios, the space complexity stays constant at 1, as no additional memory is used. To understand the efficiency of the optimized algorithm better, let's compare it with a brute force approach. A naive method might involve creating a new array to store all the non-zero elements followed by appending zeros. For this, we would first iterate through the array to collect non-zero elements, which would take n time. Then, we would append zeros to the new array to match the input size, which also takes n time. Finally, replacing the original array with the contents of the new array would take another n. Altogether, the time complexity of this naive approach is n plus n plus n, which simplifies to n. However, the major drawback is its space complexity. This brute force method requires an additional array, taking up n memory in addition to the input. In contrast, the optimized algorithm achieves the same n time complexity but with 1 space complexity, making it significantly more memory efficient. Finally, let's mathematically validate the algorithm's time and space complexity. The time complexity is linear, n, because the for loop runs exactly n iterations, where n is the length of the array. Within each iteration, the operations, such as the comparison and the swap, are executed in constant time, 1. Combining these, the total number of operations is n asterisk 1, which simplifies to n. For space complexity, the algorithm does not use any additional data structures. It only relies on a constant number of auxiliary variables, such as non_0_pos, which require 1 space regardless of the input size. Therefore, the overall space complexity is constant, 1. This proves the algorithm's efficiency in both time and space usage. When solving the move zeros problem, there are a few common mistakes to keep in mind. First, it's essential to distinguish between in-place algorithms and those that require extra space. An in-place algorithm modifies the array directly and uses 1 extra space, whereas creating a new list to store non-zero elements increases the space complexity to n. This distinction is critical because many interviewers specifically require 1 space solutions. Another mistake is overwriting elements prematurely. This happens when you start replacing values in the array before fully processing the non-zero elements, which can lead to data loss and incorrect results. Additionally, avoid the inefficiency of nested loops. Shifting zeros one by one results in n squared time complexity, which is impractical for larger arrays and unlikely to meet the problem's constraints. Lastly, always test edge cases. These include arrays with all zeros, arrays with no zeros, or even arrays of size 1. Neglecting these scenarios can lead to solutions that fail during testing. Another common pitfall is misunderstanding the problem requirements, particularly the need to preserve the relative order of non-zero elements. Reordering them arbitrarily will lead to incorrect results, so this requirement must always guide your approach. To excel in interviews, it's important to understand trade-offs. For example, a two-pointer solution offers n time and 1 space complexity, making it optimal, while other methods like a brute force approach may use n squared time or require additional space. Clear communication is also key. Explain each step of your thought process, especially when deciding between modifying the array in place or using auxiliary storage. Make sure to justify how your solution satisfies the problem constraints. A great way to impress interviewers is by optimizing iteratively. For instance, you might start with a straightforward brute force approach and then refine it into an optimal solution, like the two-pointer technique. This progression shows your ability to think critically and improve your solution. The move zeros problem shares similarities with other popular LeetCode problems, making them excellent practice opportunities. For example, LeetCode 26, remove duplicates from sorted array, also requires in-place modifications while preserving the order of elements, which is a key concept here as well. Then there's LeetCode 283, the move zeros problem itself, which we are focusing on. It's foundational and should be mastered thoroughly. LeetCode 75, sort colors, is another related problem that uses the two-pointer approach to rearrange elements in place, teaching you how to manipulate arrays efficiently. Finally, LeetCode 27, remove element, involves removing specific elements from an array while maintaining the relative order of the remaining elements. Practicing these problems will deepen your understanding of in-place algorithms and prepare you for a variety of interview scenarios. There are several ways to approach the move zeros problem, each with its own trade-offs. The brute force approach involves traversing the array, collecting all non-zero elements in a new list, and then appending zeros to the end. While this method is simple to implement and runs in O(n) time, it requires O(n) additional space, which is often not acceptable in interviews. A more optimal solution is the two-pointer approach. Here, one pointer tracks the position of the last non-zero element, while the other iterates through the array. By swapping or overwriting elements, you can achieve O(n) time complexity and O(1) space complexity, although this method requires careful manipulation of pointers. Another efficient method is the count and fill approach. In this strategy, you count the non-zero elements in one pass and then overwrite the array with these non-zero elements, followed by filling the remaining positions with zeros. This method is straightforward and space efficient, but it requires two passes over the array. Each of these approaches has its place, depending on the constraints and requirements of the problem. Great job! Today, we learned how to solve the move zeros problem efficiently, focusing on time and space optimization. Remember to keep practicing array manipulation techniques, as they are common in interviews. Thanks for watching. Be sure to like and subscribe for more content, and I'll see you in the next session. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!